确实你也没有。
他已经叫我把摘要看后文写，所以我也重测。
你们摘要是有数据没有？有。
OK，
有，我的有。
我算了那个，
我的全靠他来的，他已经
刚
给我用。
是我觉得要做大所有的这样。
我也是打算用，
也是代公司。
OK。
我代工是我
有遇到上学期。
我觉得我因为是。
不行，你要教我，要补，你不是上我
Force acceleration. Okay. Probably. Hi. So probably need only about 40 minutes to 15 minutes to finish this part. But it's important, and I think it's very exciting. Very exciting. This phenomenon is called force acceleration. The idea is that we can exert an external periodic force to keep our acceleration going. Right? We say that if there is damping, then the amplitude will become smaller and smaller. But if we want it to keep oscillating, we probably need to exert an external periodic motion force. For example, you can do this. Okay, you can just see. Okay, and there's actually a motion picture for that. So you can do this. So you can see that then the system really start to oscillate. This is a typical simple harmonic motion. Force oscillation. Force oscillation. And in nature, it occurs when there are some external force, for example, wind or earthquake. Earthquake is definitely a periodic force. Okay, so when an earthquake happens, then the Taipei 101 will start to oscillate. Okay, that's a typical force oscillation situation. Okay, so I hope that motivates you to study this phenomenon by equation. Here I will assume the external force can be written as F0 cosine omega dt. It's a cosine function, so it's periodic. So that's why I'm talking about a periodic external force. But remember, this omega d is not the same as omega. Of course, because omega is internal, is a property of the spring. It doesn't have to have anything to do with external force. Okay, right? Because the external force is exerted by me or by nature. It doesn't have to have anything to do with the spring itself. Okay, so omega d is different from omega. Remember this. Later it will become very, very important. The response, I will say, the response of the spring system will depend on the relation between omega and omega d. Mark this word. You will see very soon. Now, so with this, with the presence of this external force, we add one more term to our equation of motion. So on the right hand side, in addition to the damping force, the spring force, now we have F0 cosine omega dt. On the left hand side, of course, me times a. Okay, and as usual, I move the m to the right hand side and put everything to the left hand side except for the external force. It is easier to see the difference between two different kind of terms in this way. So on the left hand side, we have a d squared x over dt squared plus pb over m dx dt plus omega squared times x. So everything involves the function x. But on the right hand side is a function of the variable. The variable here now is time. So on the right hand side is a function of time. Okay, so on the right hand side, it does not have anything to do with x. So anything related to x to the left, anything not related to x to the right. That's the basic classifying principle. It's easier to see it this way. Okay, so this is obviously inhomogeneous according to our definition. Then that means the right hand side, the source, this fx is not equal to the, remember here x correspond to y here, t correspond to x. I told you earlier, this is the mathematician way, this is the physicist way because we are concentrating on x position as a function of time. But they are concentrating on a function y as a variable of x. Sorry, but you have to adjust accordingly. Okay. No, so if you compare the two, it is easy to see this is a second order linear ordinary equation with constant coefficients and inhomogeneous kind. Because the presence of the new term that may give you a non-zero right hand side. Okay, 这个我们就把它叫做 inhomogeneous. Maybe we'll call it inhomogeneous simple harmonic motion, just like in decay equation, we have an inhomogeneous decay equation and homogeneous decay equation, right? Okay, you will see that this inhomogeneous equation and homogeneous equation are closely related to each other. Okay, again, the force oscillation is determined by two frequencies. I told you already, omega d and omega. And you will see the response will depend on the relation between the two. And again, method 0. For the first intuition, let's ignore the damping first. You will see the result will be very, very, very revealing. Okay, very, very easy to see. Okay, but easier to calculate. For simplicity, let's ignore the damping first. So on the left, that means the B is equal to 0. Okay, so the equation now becomes d squared x dt squared plus omega squared x equal to cosine omega dt. Why did I do that? The reason is simple. It's easy to guess the solution, right? Because on the right hand side we have a cosine function. So if this x is the same cosine function, the second derivative will be the same cosine function. So this will be cosine omega dt, this will be cosine omega dt, this will be cosine omega dt. The only thing you need to do is just equate the coefficient. 你只要把它的系数搞成一样，你就得到了一个解。Simple. So again, that's why I started with ignoring the damping. The reason is simple because it's easy to find a solution. Okay, how easy? Not find. Actually, just guess by intuition. Method 0. Okay, so let's guess the solution is in the form a times cosine omega dt. Of course, you will see that omega d is the angular frequency, a is the amplitude, and the reason for guessing this, again, is the derivative and the function itself are both the same function as the right-hand side. Okay, so you have 3 identical cosine functions. You only need to, and a very important characteristic of this solution we guessed is that the angular frequency is not omega. Oh, that's a big difference. Remember, this oscillation, if without the external force, the angular frequency is omega, square root of k over m. But now, with external force, the oscillation frequency just changed totally into the angular frequency of the external force. You have to remember this. It's a big difference. Okay. 原来没有外力的情况之下，这个弹簧系统它的这个 angular frequency 呢是 omega， 根号的 k 除以 m。加了外力了以后呢，至少我们猜的这个解，它的频率完全按照外力的频率 omega d。请注意，所以这个不是原来的解，这不是我们原来在没有外力的情况之下所习惯的那个解 ，totally different. Okay, so that's why this guessing is so important because we are coming into a new territory. This is a new solution. This is a new solution. The old solution will come back very soon. You will see, but this is a new solution. Okay, so remember, secondly, let me remind you twice. This omega d is not omega, so that means the oscillation will follow the external force. So if I plug into the equation, I say the first term, the second derivative will become omega d squared by chain rule twice. Omega d prime cosine omega d taking two derivative will become cosine omega dt. Minus a stay there, plus omega squared times a cosine omega dt. We just plug in x. On the right hand side, nothing changed. F0 over m cosine omega dt. Let me put this slowly because this calculation takes a little bit patience to do. But you see that the point is all the terms are proportional to cosine omega times t. So you can just cancel out, and you immediately arrive at a condition for A. A equal to F0 over m omega squared minus omega d squared. Bingo. So we get one solution of the inhomogeneous equation of force oscillation. This solution will be called resonance solution. This solution will be called resonance solution. Of course, everyone could see that this solution is not complete because I have no way to put in the initial condition, right? 没有办法放起始条件进去啊。Okay, but I will argue later. In the long term, this resonance solution is what matters. See, in 10 minutes, you will see the result. Okay, so I hope I convince you, at least I get one solution of the inhomogeneous equation, and I call it the resonance solution. It looks like an oscillation, cosine omega dt. The oscillation follows external force, but the point is, the amplitude is not arbitrary. A is equal to F0 over m times omega squared minus omega d squared. Amplitude is not arbitrary, unlike in ordinary simple harmonic motion. In simple harmonic motion, the amplitude is xm, right? Xm you can put in any number, right? You can pull it a little larger, you can pull it just a little bit, then xm will be different. But here, no, this amplitude is fixed by F0 m omega squared and omega d squared. That's a very, very important characteristic of the resonance solution. 它的振幅是固定的，应该是说它的振幅呢是被决定的。If you want to know the amplitude, you have better know the relation between omega squared and omega d squared. Okay, so let me first study the property of this resonance solution first. Okay, resonance solution. First, I have said under the periodic external force, the response is still an oscillation. But now the frequency follows external force, omega d, instead of omega. I've emphasized enough in the earlier page, so I'll just leave it here. Second, the amplitude is not arbitrary. First, it is proportional to F0. That's easy to imagine. The larger force we exert, then the larger response. What else, right? So it is proportional to F0. It's not surprising. What is surprising is that it depends on the relation between omega d and omega. Oh, there is a denominator. In the denominator, there is a term, omega squared minus omega d squared. So imagine this omega d getting closer and closer and closer to omega. Think again, omega d is the angular frequency of external force. Omega is the natural frequency of the spring system. If the two get closer and closer, almost identical, then this A will become larger and larger and larger and larger. That's why it's called resonance, 共振。当两个频率一样的时候，两个就非常非常有强烈的感觉。That's called 共振。That's why it's called resonance. I call it the physical law of dating. Why? Because the dating will succeed only when the two resonate. That means usually means the frequency of U2 are close enough, like omega d and omega. Ladies and gentlemen, let me introduce you physical law of dating. Yeah. So some girl or man or boy like chocolate. Some of them like flowers. Some of them like something more luxurious. So when you go dating, you better understand the natural frequency of your counterpart. Okay? If not, the response will be very, very small. Remember, if omega is very, very different from omega d, then there's no resonance because this term will be very large in the denominator. So the amplitude A will be small. So if she likes chocolate and you give her luxurious watch, it doesn't work. Work? So that means you are. Okay, so I think you got my point. Okay, so you.
What if omega d is larger than omega?
It's okay because if larger than omega, I'll show you it to you later. But if omega d is larger than omega d, then it just become a negative term. So the amplitude usually means the absolute value of this. Okay. So if there is a negative term, it only change the phase. Use the jargon. 你会把那个相场数给改变而已。But the amplitude is usually when I am not very careful by calling this the amplitude. Amplitude should be the absolute value of this term. So it doesn't matter whether there is a negative term or not. But you will see some motion picture later. What will happen when omega squared is larger than omega d? Okay, so get back to the physical law of dating. So this is called resonance law, or resonance curve. And what else? So the point is, let me say it twice. The closer omega d is to omega, the larger the amplitude of the oscillation. Okay? So that's what happened in this graph. Because I cannot find a graph with only this case, so 这些都放进来了，所以 let's concentrate on this one and this one. It's no damping. It's no damping. Okay? But from this outer curve, you can see that when the omega, and of course, the horizontal line is omega over omega d. Okay, or omega d over omega, it doesn't matter. Okay, so but when it getting closer to 1, that means omega d getting closer to omega, you can see the amplitude increase rapidly. Okay, and to answer your question, if it's larger, it becomes smaller then. It falls down again. Okay, so the second reason, it falls off rapidly when omega d move away from omega. When omega d is not equal to omega, for example here, look at this point. Omega d over omega is 2. That means omega d is twice omega, or omega is twice omega d. Then it falls off from here to here. It's about 1/5. So it falls off very rapidly. Okay. So again, you better know what she or he thinks before dating. Okay. Resonance physics. Okay, now, of course, this diagram does not make any sense, right? Because you will object right away, when omega is equal to omega d, the amplitude is infinite, because then this term is equal to 0. Okay, so it's infinite. So it does not make sense. It does not happen in nature. The problem arises because I make a very unnatural assumption b is equal to 0 without damping. It does not happen in nature. In nature, there is always damping. There is always damping, friction force, right? So by ignoring damping, I generate this infinity. So if I put in the damping again, so now the damping appear again. Let me show you the result, but a systematic way to arrive at this solution will come next week. Okay, and the solution now will be again a cosine omega dt, but plus a phi, a phase constant. This is additional with the presence of damping. And most important is a changed already. A now equals to f0 over m, the same as before. but square root of omega squared minus omega d squared plus, this is the new term, b over m omega squared. So this is the new term. Without b, it becomes back to this. You get back to this. With b, the solution becomes, the curve becomes like this. So the point is, there is still a maximum. And this maximum still occurs nearby the point of resonance. Omega d equal to omega. Because when omega d equal to omega and this becomes 0, the denominator is almost at the minimum. Almost, but there is some very small difference here. Okay? So omega equal to omega d still is the resonance point, but now the amplitude is not infinite, but a finite value. So this is called resonance curve. 各位同学，这个就是你未来在学习的过程中，会一直不断的出现在你的课程里头的。The resonance point is the most often seen diagram in physical courses. In every branch, you will see this kind of called resonance diagram. I major in particle physics. In particle physics, every particle is represented by a resonance like this. Okay, particle physics is totally different from the simple harmonic motion, right? But still, the mathematics dominates. The mathematics is the same, and they still find this kind of diagram. Okay. Now, ladies and gentlemen, this is the resonance curve. The principle is that the resonance will occur, the amplitude, the maximum will no longer be infinite, and it will occur at omega equal to omega d. One more feature. In this diagram, there's a width of the curve. And this width is proportional to b. This is a very important feature, okay, or individual feature. Later, you will see that if b is large, not later, here. When b is large, you will see that the resonance no longer holds, right? Here in this diagram, I not only write one resonance curve, I write a lot of resonance curve for various resistance b. When the resistance is small, then the curve is very, very narrow. But if b becomes larger and larger and larger, you see this yellow line, you almost did not feel any resonance at all. It becomes a very curvy curve, right? So we usually say that the width of the resonance curve is proportional to b, but the damping will weaken the resonance, or the damping will weaken the resonance. Okay, so here on this page, I list all the property of a real force oscillation with damping. You can see that almost all the major property we observe in dampless force oscillation still exists here. Maybe I should say it once again. The basic feature of resonance solution without damping remains true here. The solution oscillates in the frequency of the external force, omega d, instead of omega. And the closer omega d is to omega, the larger the amplitude. But it falls off very rapidly from resonance. Ladies and gentlemen, resonance solution. Okay. Yeah, maybe I should show you the motion picture here. This motion picture shows you what I do. The first one, this is called under resonance, because omega d is smaller. Doesn't matter. When I recorded, I was speaking on the phone, so here, when omega is smaller than omega d, you can see that the oscillation is not very large. But if you go to this, and this is the diagram of its position. Now, on resonance, if omega is equal to omega d, you can see clearly then the oscillation becomes very large. In this motion, or it even become a disaster. It's outside the simulation is no longer realistic. Okay, you may say that, well, is it because the omega becomes larger then the response becomes larger? No. Here the omega becomes larger than omega d. So we call it above resonance. And you can see when you go above resonance, that's what happened. The external force moves very rapidly, but the spring does not respond. Okay. If you do not believe this motion picture, at least we have a real video. This is by the MIT physics lab. In this movie, the external force is controlled by this motor, and there is a line here represents mass and the spring. Okay, now it's under resonance, so it moves slowly. Not much response. Under resonance. Okay, below resonance. Okay, now it's increase the frequency till resonance. See, that's resonance. Okay, it respond very, very large. Now, if you increase the frequency even further above resonance, no response. That's why I say when omega move away from omega d, and the response falls off rapidly. Okay, good. So I hope everybody gets some picture of the whole thing. Okay. Resonance. Of course, here everybody wants to know the final answer. Because this resonance solution is not right, or it's not complete. We cannot put in the initial condition. 我们没有办法把起始条件放进去啊。Okay, but remember in I think it's the week before last we talked about the inhomogeneous decay equation and the decay equation. I say that the inhomogeneous decay, the solution of any inhomogeneous equation is equal to a solution for homogeneous solution plus a solution for inhomogeneous equation. Here it's the same. I can do the same thing here. I will say resonance solution is one solution of the inhomogeneous simple harmonic motion, but it could not always fit initial condition. Okay, so if there is another solution we call x, then let's calculate the difference between x minus xr. We calculate the difference between x and the xr. You will see that the x minus xr actually is a solution of the homogeneous ODE. It's easy. If x is a solution of the inhomogeneous one, I can write this. Clear? In xr, the resonance solution, of course, is a solution of this equation. And just minus. Okay. When you subtract this from here, then it is easy to see that you can combine the two derivative into x minus xr over dt squared. I usually say you can do derivative first minus second, or you can do minus first and derivative second. You can change the order. That's the essential essence of the derivative and linear combination. The second term is the same, b over m. You can do dx dt minus dr dt. You can also do dx minus xr over dt. The third term is the same, omega squared times x minus xr. The right hand side, miracle. The right hand side cancel out. Of course, it's the same solution, it's the same equation. So of course the source term must be the same. So when you subtract this from here, then the right hand side just cancel. So the same equation without source, that is homogeneous. I hope it's clear to everyone. Oh, so the difference between any two solutions are inhomogeneous is a homogeneous solution. So let me put it in English. X minus XR equals a solution, XS. Let's call it XS of the homogeneous version. Homogeneous version is this. Just get rid of the source term. But this is damping. So XS is damping, the solution of a damping oscillation I have shown in the first class today, right? So the result is simple. X minus XR equal to XS, then that means X is equal to XR plus XS. Right? So put in one sentence, solution of linear inhomogeneous ODE always equals to one solution of the inhomogeneous ODE plus the solution of the homogeneous version. This result is general. You may still remember we do the same thing in the decay equation, but here we do it again. Okay, so finally the result. This is the solution of damping oscillation. That is the homogeneous one we call XS. This is the solution we already guessed. That's the resonance solution, which is solution of inhomogeneous simple harmonic motion. And X will be equal to XR plus XS. Oh, now I understand why I want to add an XS. Because in XS, there are two unspecified constants. For this solution, there is no constant, no uncertainty. It's just one solution. It could not fit any initial condition. But if I put in an X, I add an XS into the solution, there are two unspecified constants here, Xm and phi. Let me put it in English. 这是共振解，这个是非共振解。共振解它就是一个解，你猜出来的，没有起始条件的自由度。但是你可以把它加上一个非共振解啊，非共振解是 homogeneous version of the equation 啊 ，OK， 所以它本来就有两个自由度。以这个实际的例子来说，就是 Xm 跟 phi 啊，这两个没有确定的 constant 就可以让你来 fit initial condition. This is the most important thing I want to say today. Okay, so with resonance solution, we add a non-resonant solution, and we can adjust the constant Xm and phi in XS to satisfy the initial condition. And we are done. So this function XR plus XS not only satisfies the inhomogeneous simple harmonic motion ODE, but also the the initial condition simultaneously. So we are done. It's a unique solution. Any question? 今天最重要的结论就是这个。So force oscillation is done. It's complicated, maybe. Yeah.
为什么求得那个 XS 的方式是把 X 减掉 XR？ 就是为什么把这两个东西减掉，你就可以得到一个？
不，因为我减掉了when I subtract XR from any solution, if I form this combination X minus XR, and it satisfies the homogeneous version, it's here. 就是我如果把它减掉了以后，它事实上满足这个方程式啊。这个方程式不就是 homogeneous version 吗？看一下，就是这个括号就是一个 x 啊。
可是你说你减掉，你就可以得到一个方程式，它是可以有起始条件的。
没有，这个 xs 的这个解是有起始条件的。应该是说 it's a complicated 那个 formula. But remember, all the notations in XR are constants, but specified. 都被决定了 omega d is omega d, phi is the formula before, and everything else are determined. However, in XS, there are two constants that's not specified, which is xm and phi. That's the point. 在这个 let me put it in English, in Chinese. 在这个方程式里头，所有的东西都是决定的。当然啊 ，OK, you can check one by one. 所有东西都是有 formula 的，都是被决定的。但是在 XS 里头，它有两个数是没有决定的啊 ，xm 跟 phi 啊。OK, xm 跟 phi 是没有决定的啊。因此，我就可以 therefore, because there are two unspecified constants in XS, then I can use these two constants to fit the initial condition.
So the XS just works as the uncertainty, or
It's not uncertainty. There's uncertain constants, but the uncertain constant is for us to fit initial condition. By fitting initial condition, that means I can find xm and phi that satisfy the initial condition. You can adjust xm and phi so that x0 is equal to the initial position and x prime 0 equal to the initial velocity.
what is XM for?
Sorry?
What is XM for?
Amplitude. So it's just a notation.
Oh, okay.
But remember, I know the solution of the this is a damping oscillation. The damping oscillation equation of motion. Remember, we covered in the second part. And I show you the result is like this. At that time, I say the amplitude decrease, and it's still oscillation, da 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 da. And remember, this xm is the initial amplitude. It decreased, but what does it decrease from? There must be a starting point. Or if you want to show you, let me go back. So that xm is this. Here, yeah. When time is equal to 0, this is xm.
Oh, the maximum point.
The maximum, yeah. After that, it decreased. But this is a constant I can specify, I can adjust, right? I can adjust it to our initial condition. And also phi is also adjustable. So there are two unspecified constants. I hope it answers your question. Okay, so that's the beauty of this solution, XS, inside our final solution. Remember, XR has no uncertainty. Because everything in XR are specified. Because they are just constant everywhere. Okay, omega d, b, f0, m, everything are determined. It's given by the problem. But in XS, there are two unspecified constants. Okay, so we can adjust these two unspecified constants so that the answer x satisfies the initial condition. Okay, maybe I will write down the general formula. When I write down the general formula, you will understand, even though that general formula probably is not that useful. Okay. Okay, but hope you can accept the final conclusion. XR plus XS satisfy the inhomogeneous simple harmonic motion and the initial condition simultaneously. Okay, so this is the single solution. But that's not the answer. That's not the conclusion today. If you look at XS and look at XR, you suddenly realize that XS is not important. Why? It's simple, because it decays. but this term does not decay. Is that clear? Because there is an exponential minus b over 2mt. So when time progresses, when time progresses, the amplitude will decrease exponentially. However, XR, the resonance solution, does not decay at all. It keeps on oscillating because the amplitude does not depend on time. So it oscillate and oscillate and oscillate and oscillate. But the first term decreases very rapidly. Maybe after 1 second, maybe after 2 seconds, it disappears. So I call it initial condition does not matter. 你的出生不重要啊，你起始条件一点都不重要啊。In Chinese, okay, it means your birth background does not matter. Background means your initial condition. In this solution, the initial condition does not matter at all. If you don't believe me, let me try to give you a simulation. This is a simulation of force oscillation with 2 different initial conditions. This one, we start from the rest and start oscillating. It takes a while, sorry, but I hope you can see the motion directly. So after this spring system is driven by external force and undergoes an oscillation. And if you can see the data, the frequency is the frequency of the external force, not omega, it's omega d. Okay, it needs a while. But you can see that initially it does not look like a single oscillation. But after a while, it becomes a standard oscillation. The amplitude does not change at all. I hope it's clear from this point. Now, if I change to a second set of initial condition, here I pull the spring downward and let it go. 不同的起始条件 is a different initial condition. Okay, so in the beginning, it is different from the first one. But it's misleading. After a while, it becomes the same. So the initial condition is wiped out. Only the external force matters here. How? Okay, then here, to save your time, I put the 2 diagrams together with longer duration, and you can see again, initial condition are different. And so the initial response are definitely different, but after a while, you cannot see the difference between them. And this is the resonance solution, because XS has disappeared. And what remains is XR. That's why we spend so much time on XR. That's because that's what matters. Okay, so let me remind you the final time. The X resonance solution is this. The frequency is omega d. The frequency of the XS is also an oscillation, but the frequency is omega prime. So that's a major difference. Okay, so that's why in the beginning, the 2 oscillations mix together. So in the diagram, you see initially they mix together. It doesn't look like an oscillation at all. But after a while, it becomes one solution, or one oscillation. That is this term, because the first term disappeared. Only this term will matter, and the angular frequency is the external force. And of course, this is very similar to what we have in the inhomogeneous decay equation. Remember, when we solve the inhomogeneous decay equation, we also have 2 terms. One is this, one is this. Mg over k is one solution of the inhomogeneous version. The front one, c times exponential minus k over m times t, is the solution of homogeneous one, so that there is a C unspecified constant for us to fit the initial condition. But in the long term, again, this term disappears because when time becomes larger and larger, this term just vanishes. Only the mg over k will stay. That's the terminal speed of free falling. Okay. I hope you can compare the two solutions and see the connection between them. Okay. What else I can say? Oh. Yeah, the rest I can wait until next week. Next week I'm going to show you a lot of examples. Okay, today only field mathematics, but next week I'll show you a lot of examples, including these very interesting. Yeah, maybe before I let you go, maybe show you this. This is so-called breaking glass with sound. Here, the sound is the external force, and the glass is an oscillate, is a 变形, a transfiguration of the glass. So there is an angular frequency. So you can think of the glass as a spring system. 把它当成是一个弹簧。So this guy carefully put on glass. It shows you how to oscillate a glass without touching it. You use the sound from 从一个喇叭然后放出声音出来。And then in the beginning, there's not much response from the glass because there's no resonance. But now, not only change the volume, he also change the frequency. Bear with it a little bit. He changed the frequency. Well, the frequency are same. Okay, give me answer. So, that's slow motion. So you can see the oscillation of the glass without touching it by sound. High speed video. By sound. So that's resonance. Break. Don't you think there's a beauty in it?
Is this like a Bromian motion as well?
Huh?
Is this an example of a Bromian motion?
I hope you enjoy it. Okay, see you next week. So that's resonance. You have to adjust the frequency of the sound to the frequency of the oscillation of the glass. Okay. Next week, more example. And then we'll go to the systematic way to solve the equation.